Hi, I'm Alan Bowling from the Department of Mechanical and Aerospace Engineering at the University of Texas at Arlington. This presentation is a two-part series about 2D vectors in engineering. So let's get started.
So here's a real-world problem. We want to travel from this point on the map to this point on the map, and we want to investigate the distances involved in making that journey. So we can do that by translating this problem into the mathematical world. So let's begin. Okay, so one of the first things we do when we translate things into the math world is to simplify. So here you see we've taken out all the trees and the yard and the grass and all that stuff, and we just have the street map left over. So we wanted to move from here, which I'm going to label point A, to over here, which I'm going to label as point B. Okay. However, when we simplified this representation of the real world, we lost some information. So I'm going to put that information back. And one of those pieces of information looks like this. As you might guess, that looks like north. What you would typically see on a map is north. And this arrow here is what we call a graphical representation of a vector. And this graphical representation typically has a tail, call that the tail, and this is called the head of the vector. So we also need some other information. I'm going to put that here, and this is what you might guess is east. That's what we would call east. So when we do our graphical representations, we use these arrows. However, when we do the math, we're going to use these symbols to represent the directions north and east. And you'll also notice that we only have two directions here, and we can use these two directions to describe all of our movements on this map. And we would say this map is a plane, so north and east are sufficient to describe all our movements along this map. So because of that, there's only two directions, so we call this a 2D vector. Okay, so if we wanted to move from point A to point B, we need some directions on how to go. And that set of directions might look like something like this. Go north on Miller Avenue, and then go east on Ramey Avenue to South Hughes Avenue. Okay, so if we have that, if that's our real world list of directions, that path looks like this. And we would travel up here to here, and then we would travel over to get to point B, like that. So what we want to do is take this list that we would get in the real world, and translate it into the mathematical world. So let's do that. Okay, so let's start again. This is our point A. This is our point B. And I'm going to add an intermediate point, which I'll call C. And I'm going to put back our directions, north and east. So we want to start to develop our directions in mathematical form. So the first direction was to move north on Miller Avenue, but I don't want to refer to Miller Avenue anymore. I want to use my math. So I'm going to make a distance that I'm going to call X. And for now, we're going to assume that all these streets align with north and east, even though they may look like they curve a little bit or something, but we're going to assume that they're all straight and they line up with north and east. So I'm going to make this other distance that I'm going to call y. Okay, and now I want to take that list of directions and convert it into math by making a first vector, which I'm going to call A to C. That was the first leg of the trip up Miller Avenue. And I'm going to say I'm going to walk x distance in the north direction. And that takes the place, that's the mathematical representation of that first direction in the list of directions, real world list of directions. The second vector takes the place of the second direction, which is PC to B, which is to move y in the east direction. Okay. And now if I want to move from P, if I want to figure out how to get from A to B, I represent that as the vector addition of A to C plus C to B. So that is the physical representation, that is the mathematical representation of moving from point A to point C and then over to point B. So we represent that physical thing with a vector addition. I can also plug in the definition again, and you get something that looks like this. Y in the east. That's what it looks like in the math world. Graphically, if we want to do this graphically, we can do this. So we make that vector, and we call that vector P A to C. And then we go make this vector here, which we call P C to B. And then we add them to get A to B. And A to B is this one. It looks like that. P A to B. So that's what graphical vector addition looks like. You take the tail of one vector and you put it on the head of the other vector, and you draw the result from the first tail to the last head, like so. It looks like that. You can also look at this guy again, and we call these two things components. So x is the component of PAB in the north direction, y is the component of PAB in the east direction. So now we have looked at vector addition mathematically and graphically. So in summary, we learned how to compose a 2D vector to represent physical quantities like walking from one point on the map to another point on the map. We also learned how to do vector addition mathematically and graphically. So please watch part 2 so we can learn about distances, which is the original problem we wanted to investigate. Thank you for watching.